It began with a flicker. One green dot on a screen representing a Starlink satellite suddenly blinked out. No warning, no scheduled deorbit, no sign of collision. The satellite simply went dark. Teams scrambled to re-establish contact, sending commands into the void, but silence persisted. This was no ordinary malfunction. Whispers of laser began to circulate. The incident occurred over the Pacific, a region watched by many nations where geopolitical tensions run high. The idea of a silent, invisible attack, leaving no debris, just a dead satellite, was chilling. Suspicions turned to space powers with advanced directed energy programs. The event felt like a shot fired in a new kind of war, waged with beams of light in the cold of space. Was it an accident, a solar flare, or the first move in orbital warfare? Official silence from governments and the company only deepened the mystery. Intelligence agencies launched a frantic search for answers, focusing every sensor on the patch of sky where the satellite vanished. The world held its breath, reminded of the fragility of our technological constellations. Our global communications web, the backbone of modern life, is more vulnerable than we care to admit. In the darkness above, a single point of light had gone out, and with it, a sense of security. The age of contested space had arrived. The truth, when it emerged, was both less and more dramatic than the rumors. There was no attack. The Starlink satellite's failure was a technical glitch, not sabotage. But while the world chased shadows, something far more significant happened. Chinese scientists had used a laser, not to destroy but to communicate with a satellite in geostationary orbit, 36,000 kilometers away. They achieved a stable, high-speed data link at 1 gigabit per second, a feat never before accomplished at such distance. This wasn't a weapon, but a focused stream of pure data. The narrative shifted from military threat to technological leap. The Chinese team had solved one of the hardest problems in optical communication, sending a coherent beam through Earth's turbulent atmosphere to a tiny target in space. Space agencies and telecom companies worldwide took notice. This was a paradigm shift, proving that high-bandwidth communication from GEO is now possible and efficient. The feared beam of light was a message. The race for space communication dominance had entered a new phase. The future of orbital infrastructure had changed overnight. The most astonishing detail? The laser's power, just 2 watts, less than a refrigerator bulb. How could such a tiny amount of energy bridge 36,000 kilometers? The secret is focus. Unlike a candle's glow, a laser concentrates every photon into a narrow, coherent beam. In space, with no air to scatter it, that beam travels with near-perfect efficiency. The result, a clear, detectable signal at the satellite, not a dim glow. Laser communication, or lasercom, is revolutionary because it transmits huge amounts of data using a fraction of the power required by traditional radio systems. For power-starved satellites, this is a game-changer. Less power for communication means more for the satellite's mission, and smaller, lighter, cheaper satellites. The Chinese demonstration proved that a whisper of energy can shout across the cosmos. It's a new era of hyper-efficient space infrastructure. The implications for satellite design, cost, and capability are profound. With the right technology, even a faint beam can carry a torrent of data. The future of space communication is laser-focused, literally. The real challenge isn't distance, it's Earth's atmosphere. Turbulence scatters and distorts light, threatening to turn a focused laser into noise. Enter adaptive optics technology that measures atmospheric distortion in real time and corrects it with a deformable mirror. The system acts like prescription glasses for the sky, adjusting thousands of times per second. The Chinese team combined this with mode diversity reception, using multiple receivers to capture scattered photons. Together, these breakthroughs tamed the atmosphere, making low-power, long-distance laser links possible. They didn't just punch through turbulence, they mastered it. This is what enabled their record-setting communication. The Chinese breakthrough highlights a strategic crossroads for global networks. The dominant model, LEO megaconstellations like Starlink, uses thousands of low-orbit satellites for low-latency, high-redundancy coverage. But this approach is costly, complex, and adds to space debris. China's demonstration points to an alternative: geostationary sentinels. GEO satellites, now empowered by lasercom, can provide continuous coverage over vast areas with just a few satellites. High-bandwidth, low-power laser links make the GEO model newly competitive. Fewer satellites mean lower costs, simpler management, and less debris. It's a different philosophy, not a swarm, but a few powerful eyes in the sky. The future of global connectivity may hinge on which model prevails. The race is on to redefine how our planet stays connected. The stakes couldn't be higher. Starlink has become critical infrastructure connecting the unserved and underserved worldwide. In disasters when ground networks fail, Starlink restores communication for first responders and communities. Its resilience makes it a digital lifeline, vital when all else is lost. In Ukraine, Starlink's rapid deployment gave the military secure command and control and civilians a link to the world. The network's dual-use nature, civilian and military, makes it both powerful and a target. Control over information flow is control over the modern world. A network that can reach anywhere is an instrument of immense influence and vulnerability. The security of these systems is now a matter of urgent national concern. Every leap in technology is a double-edged sword, and Lasercom is no exception. On one side, it promises global high-speed internet, real-time Earth observation, and a revolution in space exploration. Missions to the Moon and Mars could send back data in real time, accelerating discovery. But the same precision that enables communication can also blind or disable satellites. A soft kill, with no debris. The line between tool and weapon is razor thin. This dual-use potential drives an arms race in space, with nations developing both lasers and countermeasures. The sky risks becoming a domain of invisible threats and silent skirmishes. The promise of connection is shadowed by the specter of conflict. The future of space hangs in the balance. China's Lasercom breakthrough sent shockwaves through the global space community. For defense officials, it signaled a closing tech gap and triggered urgent reviews of space security. Commercial space leaders were forced to rethink their business models and satellite defenses. Allied nations worried about being caught in a new tech rivalry, spurring calls for international cooperation and norms. Scientists celebrated the technical achievement, seeing new possibilities for research and exploration. Yet even in excitement, there was caution. The same tool that unlocks discovery could become a weapon. The world must now adapt to a reality where space technology is both a bridge and a battleground. The stakes for security, commerce, and science have never been higher. We stand at a crossroads, looking up at a sky transformed by technology. The Lasercom breakthrough is a signpost. Will space be a domain of shared discovery, or the next battlefield? One path leads to global connection, scientific progress, and cooperation. The other leads to militarization, rivalry, and the risk of orbital conflict. The choice is not inevitable. It depends on decisions made today. Technology is neutral. Intent determines its impact. As we push boundaries, we must also build trust, treaties, and responsible norms. The stars have always inspired unity. Can we carry that spirit into the cosmos? The ultimate test: will space remain a source of wonder or become a theater of war? The future is ours to shape, together or divided.